In this next video, we'll be talking about solving definite integrals using integration by substitution. So first, let's review the Fundamental Theorem of Calculus, Part 2. It says that if capital F of x is an antiderivative of little f of x on an interval from a to b, then the integral of f of x dx from a to b is the antiderivative evaluated at b minus the antiderivative evaluated at a. For our first example, let's look at the integral from 3 to 5 of the function 7x minus 3 squared. So what we'll do is we're going to first need to find an antiderivative of 7x minus 3 squared. So to do that, we're going to look at just the integral of 7x minus 3 squared. So doing a U-Substitution will let u equal 7x minus 3, then du will equal 7 dx. So this integral becomes the integral of u squared, and then what we have remaining is dx, which we can express as 1/7 du. So now rewriting this, we'll have 1/7 times the integral of u squared, which, applying the power rule backwards, is 1/3 u cubed, which is 1/3 u cubed. And we're going to leave off the constant of integration here because we're going to be going back and putting this into our definite integral. So this will be 1/21 times, and doing a back substitution, 7x minus 3 cubed. So now this is our antiderivative of 7x minus 3 squared. So by our fundamental theorem, this integral now becomes 1/21 times 7x minus 3 cubed, our antiderivative, evaluated between 3 and 5, which is 1/21 times 7 times 5 minus 3 cubed minus 7 times 3 minus 3 cubed. So now if we were to calculate this right here, we would get 26,936, and we have over 21. We could approximate this by 1,282.67. For our next example, let's look at the integral from e to the 7th to e to the 11th of 1/x times the square root of ln of x dx. So again, we need to find an antiderivative of 1/x times the square root of ln of x. So over here, let's look at integrating 1/x times the square root of the natural log of x dx. So in order to solve this, we'll need to use substitution. So let's let u equal ln of x, then du will be 1/x dx. So if we make this substitution, we'll have 1 over the square root of u. If we look at what's remaining, 1/x dx, we'll see that that is actually identically equal to du. So now, rewriting this, we are actually integrating u to the minus 1/2 power. Applying the power rule backwards, this will be u to the 1/2 power, multiplying by the reciprocal, 2. And again, we're not going to put in our constant of integration because we're going to be feeding this back into a definite integral. So this then, doing a back substitution, will be u times the natural log of x to the 1/2 power. So now we've found our antiderivative over here. We can apply our fundamental theorem of calculus, and this definite integral would be 2 times, and I'm just going to write the square root of ln of x here, evaluated between e to the 7th and e to the 11th. So now, putting in the e to the 11th, we'll have the square root of the natural log of e to the 11th minus the square root of the natural log of e to the 7th. Well, since the natural log and exponential functions are inverses of another, the natural log of e to the 11th is just 11, so this is going to be 2 times the square root of 11 minus, and again here, this will be just the square root of 7, so minus the square root of 7, and this right here is our exact answer. Now let's look at another way of solving definite integrals using use substitution, where we change the limits of integration. So these right here are x limits of integration, and we're going to now change them to u limits. So if we do our use substitution and we have u equals x squared plus 1, then du will equal 2x dx. So for our substitution here, we will have the integral of u squared, and what we have left here is the x dx, which is identically equal to 1/2 du. So we replace the x dx with 1/2 du. Now before we can set these two integrals equal to each other, we need to change our x limits to u limits. So over here, we look and we say, well, if x equals 0, then u will equal 0 squared plus 1, or 1. And if x equals 3, then u will equal 3 squared plus 1, which is 10. So now we have the integral from 1 to 10 of u squared times 1/2 du, and these two integrals are now equal. So when we solve this, we will have 1/2, and then applying the power rule backwards, 1/3 u cubed. And now, because we have u limits of integration, we do not do the back substitution. We simply use the new u limits, and applying the Fundamental Theorem of Calculus here, we'll have 1/6 times 10 cubed minus 1 cubed. So 1/6 times 1,000 minus 1, or 999/6. Now let's look at this problem. Suppose we're told that we have a continuous function and we're given some information about the integral of that function, namely that the integral of that function from 0 to 8 is -16. And we're asked to find the integral of the f of 4 of x on the interval from 0 to 2. So how do we go about doing that? Well, what we need to do is somehow transform this integral that we're trying to find and into something where we have information about it. So let's look, and here we see a 4x, and here we see an x. So let's do a u substitution and let u equal 4x. Then du will equal 4 dx. So applying the substitution here, we will have the integral of f of u, and what we have remaining, dx, is equal to 1/4 du. So we replace the dx with 1/4 du. And now let's go ahead and change the limits of integration. So when x equals 0, we have u equals 4 times 0, or 0. And now when x equals 2, we have that u equals 4 times 2, or 8. So now the integral from 0 to 2 of f of 4x dx equals the integral from 0 to 8 of 1/4 f of u du, which is the same as 1/4 times the integral from 0 to 8 of f of u du. And this right here is equal to -16. By the property of definite integrals, the integral from 0 to 8 of f of u du is the same as the integral from 0 to 8 of f of x dx. So then our final result will be -4.